Okay, so this is a question about revolving a circle around a line, and the circle is x squared plus y squared equals r squared. And this problem essentially splits into two pieces because this line, you're thinking of it as this is just a big donut. Actually, you've got a big donut that you're creating, but that point in the middle is present. There's no punch through, so it's a donut that's so big that it's just a figure eight when you slice it down the middle. Okay, so what we're looking at is we want to look at these little dx slices. Okay, so you're going to split this into two different integrals. You're going to have this inside thing where you need this little green line is going to be your radius. Okay, so that's the gap you're looking at. It's going to be, so first of all, let's figure out what this function is. This function here is going to be y is equal to plus or minus square root of r squared minus x squared. That's what the two functions are going to be, the upper and the lower part of the circle. So for the upper part of the circle, this little green line is going to be the radius of your cylinder. And when you're on that part of the surface, the radius is going to be r minus the upper part of your circle. Okay, but when you're on the bottom half of the circle, you're going to have the bottom half of the circle, and then that distance has to be added to r. Okay, so you have two different, and let me draw a little picture of that. So that's going to be going all the way back up. Okay, so you have two separate integrals. You have, let's call it area 1, or let's see, S equals S1 plus S2, since they're surface area questions. And then let S1 be the integral 2 pi times r, which is, so r in the main formula, so the surface area of a cylinder is 2 pi r times dx, right? But then you have to account for the arc length because that comes into play too. So you need the arc length piece, and you need the dx piece, and you need this height here, which in your main formula in the textbook is just f of x. But we can't use just f of x anymore because that would be misrepresenting where our axis of rotation is. Okay, so we're going to put in all these pieces. So first of all, we need to take the derivative and square it and add 1 and then take the square root. So that's going to be a pain, and that's going to go in here. And then the other piece in the first integral is r minus square root r squared minus x squared, just like that. And we're going to integrate from minus r to r, and S2 is going to look very similar. And our integral piece is going to look the same, so it'll do double duty. But then we're going to have r plus r squared minus x squared. This piece, there we go. Okay. So let's go ahead and find out that arc length piece. Okay, the y is equal to plus or minus, so may as well do 2 for the price of 1. Okay, the derivative is equal to 1/2 mass to the minus 1/2 times 2x. So the 2's are going to go away, the 2 and the 1/2. Y prime is plus or minus x over square root of mass. Okay, and then when we're going to square that guy, we're going to get x squared over something that looks slightly nicer. Okay, so I'm going to just keep going here. If I add 1 to the mess, it's just, I forgot the minus sign. There was a minus sign. There was supposed to be a minus sign in here. There we go. Okay, it would help if I just worked a teeny bit more slowly. That's the minus sign I was missing. Whoopee. That looks a lot better. And because obviously when I go to square this thing, the minus sign is going to go away anyway, so that wasn't helping me any. Okay, so if I add 1, it looks like this. Ding, ding. And if I take the square root of that mess, lucky we're getting a 2-for-1 sale on this because it's really, really annoying, isn't it? Okay, so we have this little piece, and we would like to put it in here and here. There we go. Maybe squeeze it in here and put another copy of it over here. Okay. Great. So we see these two integrals look very much alike. You see there's a certain, would be nice if we could put it together, right? Because we're looking and we're seeing this little piece and this little piece look like they should annihilate each other, but let's just, they will, but we have to be careful that we don't do something too hasty. Okay, so we're going to be, well, let's go ahead and do it, but let's be careful. Okay, so if we distributively multiply these pieces, it's the same as if we distributively multiply these pieces, so you get 2 copies. So we get 2r squared over mass. And then these pieces we distributively multiply, and those pieces should be exactly opposite. Okay. And now we can use a formula, or soon we can use a formula out of the book. Okay, so let me just recopy this a little bit. I seem to have lost, there we go. Oh yeah, this is getting messy. I'm going to cut this piece and move it because it's kind of messy. A little bit better. Okay, so now what can I do? Well, I would like to just make this a little bit neater. And since r is just a dummy variable, I'm going to put r squared outside and do something like this. Okay, then I'm going to look up reference page 6, formula number 16. And that gives us all these things that look very much like that. In the book, where we have an R, the book has an A, and where we have an X, the book has a U. So other than that, we're home free. The book says this is arcsine x over r x over r, and we're going from 0 to r. So we get arc sine of 1 minus arc sine of 0. Arc sine of 0 is 0, and arc sine of 1 is pi over 2. Let's remember why that is true. This is what sine looks like. A little piece of it goes from -1 to 1. angle whose sine of 1 is pi over 2. So that's how we know. So what we end up with is 8 pi r squared times pi over 2, 4 pi squared r squared, as promised. So that was a bit of a mess, but you know, hopefully that was useful. Again, I want you to imagine this. The important thing is imagining it. And if you only do the top part of this circle, then you'll end up with an answer that's quite a bit different. And that's what I did the first time. I forgot the other half of the circle. So anyway, if you make mistakes like that, you're in good company, but you need to fix them. Okay, have fun.